Hello everyone, this is Homer White, back again for part 2 of the 6th chapter of our book. It's called The Design of Studies. We'll divide this part into 2 separate video lectures. In this first video lecture of part 2, we'll cover completely randomized designs. The remaining parts will be for a separate video lecture. Always remember to make sure that you've loaded the necessary packages. So in part 1, we laid out the ideal of an experiment, which was to try to arrange things so that the treatment groups would be as similar as possible with respect to all characteristics of the subjects that might have some influence on the response variable. The only difference between the treatment groups, ideally, would be in the values of the explanatory variable that you've assigned to the subjects. Now, there are several ways to approximate this ideal, although it can never be achieved completely in practice. And the first such way that we'll discuss is a completely randomized design. So, trying to approximate this ideal, you would think that if you want to arrange for the subjects to be as similar as possible, then you would use your judgment entirely in order to assign subjects to treatment groups. But surprisingly, that can be a very bad idea, and in fact it's not how we do things. If we use our judgment and make our own choices about who to assign to groups, then it's quite possible, especially if we have a vested interest in the outcome of the experiment, to do the assignment in such a way that the experiment turns out how we want it to turn out. We really need to remove our judgment from the situation at some point. So, at some point, we're always going to use chance, at least in part, in order to approximate the ideal of making the subjects in the different groups to be as similar as possible. In a completely randomized design, there's minimal use of judgment. The subjects are divided into the available treatment groups solely by chance. The idea of a completely randomized design is this. If a treatment group, if say one of the treatment groups is to have size M, then every set of M subjects has to have the same chance to be that treatment group. And the same rule applies to every treatment group that you plan for the experiment. You can see that this is very like simple random sampling. Let's construct a hypothetical example. Suppose that we plan to do an experiment on whether aspirin reduces the risk of heart disease. And let's suppose that the first 200 members of the data frame ImagePop in the TigerStats package have agreed to participate. We can isolate the first 200 rows of ImagePop, that's the first 200 subjects, in the following way. We take the data frame ImagePop, and in square brackets, we ask for the rows 1 through 200. After the comma, we don't ask for anything. That's a blank there, or nothing. This is a way of saying that we would like to pull off the first 200 rows, but that we have no opinion about the columns, and we'll take them all. We put the results into something that reminds me of the name of the experiment, so aspirin heart subjects, or ASPHART subs for short. Now, our plan is to do a completely randomized design, and we have 2 treatment groups in mind here. One group is called the aspirin group, and their treatment is to take aspirin pills. So the value of the explanatory variable for this group is aspirin. And let's say we plan to put 100 out of our 200 available subjects into that group. The other group is called a placebo group. And their treatment is that they're going to take fake pills, pills that look and taste like aspirin. So that constitutes the remaining 100 subjects in the experiment. The assignment of subjects to these groups will be done completely by randomization. So we'll pick 100 subjects at random for the aspirin group. The remainder will be in the placebo group. Now, how are we going to accomplish this randomization? The package tigerstats has a function called randomexp for random experiment. The way it works is that you provide as the first argument the data frame for which you want to do the completely randomized design. After the comma comes a second argument called sizes. This says how many groups you want and what the sizes of the groups shall be. What you do is create a list of numbers. The length of the list says how many groups there are, and the numbers in the list say the group sizes. The numbers in the list have to add up to the number of rows in the data frame. There are 200 people. We have two groups of size 100. All is well. The third argument is groups, and it simply says what the names of the two treatment groups shall be. The length of this argument is the same as the length of the sizes argument, so that the group names and the number of groups match up. So although it appears in several lines, all of this is one function, and it will do a complete randomization for you. Now, you might wonder what is the purpose of the function immediately preceding, the setSeed function. Well, the way randomization works in a computer, if we were to run a function that involves any kind of randomization more than one time, we'll get different results each time. And that's fine if you want to just sort of see how complete randomization works and what sorts of different results it might deliver. But when it comes time to actually randomize your subjects into groups in a real experiment, you need to do so in a way so that other people can see how you did the assignment. You do this by setting a seed. Once you set a seed, then the assignment, although random and not really predictable by you, is completely determined by that seed. What you should use as your seed is an integer, and you can choose just about any integer at all, but it's a good idea to choose an integer that has a pattern in it or has a meaning for the folks to whom you propose to show your results. That will convince people that you haven't just played around with lots of different seeds until you found an assignment that makes the experiment come out the way you want it to come out. So I chose a number with some pattern in it, 1, 2, 3, 4, 5. There are plenty of other numbers you could choose. Let's apply this code and see how it works. So we copy, we head to RStudio, paste the code, and run it. It's run successfully, and if we look in our global environment, we will indeed see an object called assignment. Notice that it has 200 rows, just like aspirin heart subs does, but it appears to have an extra variable. It has 9 variables instead of 8. Let's take a look at assignment over in the source files pane. In the original ASPART subs, the row names went from 1 to 200, but notice now it looks like there's some kind of random removal of row names. What's happened in the random assignment of subjects into groups is that after the assignment was made, the subjects were sorted by their treatment group. That's the new 9th variable. So the 100 folks in the placebo group come first. And as you scroll down, you'll see the 100 folks in the aspirin group come second. Now remember, the goal of an experiment or of an experimental design is to make the group similar with respect to every variable that might have some impact on the response variable. Now, we can't discuss every variable that might possibly impact the response variable whether or not one gets heart disease, but there are a couple of variables that have been measured on subjects in ASPART subs that we could look at. For example, their sex. It could be that your likelihood of getting heart disease is determined in part by your sex. So it would be a very good thing if both groups were similar with respect to sex. That way, sex couldn't be a confounding variable in the study. So let's check it out. Is there much of a relationship between sex and treatment group in the assignment group? We run xtabs to see. And here's our two-way table. And we take row percents. And what we see is that there's not much of a relationship between sex and treatment groups. With regard to sex, it looks like the treatment groups are pretty similar. For example, 51% of the placebo group are female, and 56% of the aspirin group are female. Income is another possible confounder one might worry about. We know that folks with higher incomes tend to have better education, and therefore tend to learn about and adopt healthier lifestyles that might reduce their risk of heart disease, quite independently of whether they take aspirin or not. So it would be desirable if the two groups look similar with respect to income. Since income happens to be measured on the subjects in a MatchPop, it's measured on the subjects in assignment, so let's take a look and see if income is related to treatment group. We rather hope it's not. So we run favstats on income broken down by treatment group for the assignment data frame, and you get more output than you see here. Here we show just the median and the mean for each of the two groups. And let's just compare the means. The mean for the placebo group is $39,215 a year in income. The mean for the aspirin group is $39,486 a year. Those are pretty similar numbers. It looks like the two groups are pretty similar with respect to income. So income won't be a problematic confounding variable in this study. Now we had 200 subjects available for study. That's leaving 100 for each group. What we've got is a lot of what's called replication. An experiment is said to involve replication if each of the treatment groups contains more than one subject. But the more replication you can have, the better. Now there are two reasons why replication is a good thing. The first reason is, the more subjects you have, the more likely it is that the randomization process will produce treatment groups that are similar to each other. We've already seen that in the case of sex and income. Statistical theory actually says that the larger the number of subjects is, the more likely the treatments are to be similar with respect to any given variable, and in fact, the more similar they are likely to be with respect to that variable. So with very large number of subjects, you can have some reasonable assurance that for many, and maybe even all, characteristics that might influence the response variable, the treatment groups are pretty similar or perhaps even quite similar. The second reason is a little more subtle and deep, and it has to do with our notion of causality in the first place. So let's review that notion. Remember, in the first part, we said roughly that x causes y if there exist two different values, x1 and x2, of the explanatory variable x, so that whenever two people A and B are alike in every way, except that A's value of x is x1 and B's value of x is x2, then the distribution of y for A is different from the distribution of the response variable y for B. So for example, in this aspirin experiment, we would probably say that aspirin causes reduced risk of heart disease if we could somehow show that if two people are alike in every way, except that one takes aspirin and the other does not, then the one who takes aspirin has less chance of getting heart disease. But in practice, we could never find two people who are exactly alike. And also, with just two people, we would not be in a good position to estimate very well the chance of heart disease for either one of these people. After all, even if aspirin does have some causal role in reducing risk of heart disease, it's not the only thing that determines whether you get heart disease or not. It's one of many factors. So if somehow we could find two people that were exactly alike, and give one of them aspirin and the other not. If the one who took aspirin did not get heart disease, and the one who did not take aspirin did get heart disease, we still would be not sure at all that aspirin reduces your risk of heart disease, because there were so many other factors that play in to these folks getting heart disease. Perhaps it was the other factors that had the effect and not aspirin. So just working with two people alone doesn't help us estimate those chances very well. If a person gets heart disease, your estimate of the chances basically is 100%, but you know that's not right. If the person doesn't get heart disease, your estimate of the chances is 0%, and you know that's not right either. You need a better way of estimating those chances. And so what we do is settle for two groups instead of two exactly similar people. If the number of subjects is very large, and if we have randomized the subjects into those treatment groups, then we can be pretty sure that the treatment groups are pretty similar, and so that's an approximation to the ideal of looking at two people who are exactly similar. And also, we can use the outcomes for the members of each group to estimate the chance of heart disease for each group. When we have 100 people in the treatment group taking aspirin, and let's say that 10 of them get heart disease, our best guess at the chance of heart disease for aspirin takers is 10%, and we feel a little bit more confident about that guess because it's based on such a large number of people than we would on any guess that we made on the basis of one person. So if the estimated chances that you get from each group are different enough, then maybe you could ascribe that difference to the aspirin. So that's the second reason why replication is such a good thing, is that it puts us in a situation that's approximately similar to the ideal situation of looking at two identical people, treating them differently with respect to the explanatory variable, and then seeing what is the distribution of the response variable for those people. Basically, we approximate people with large groups. In the next video lecture, we'll pick up with randomized block designs.